this homework back. Yeah, 6 o'clock. What's today? Thursday? Yeah, 6 o'clock Wednesday. A long time ago.
I guess it depends what proctor you have. Yeah.
I got an extra cool. Hey.
Well, because I didn't have to stay at West Williams till tonight.
Is that an option?
Okay, so good morning, everyone. So today we're going to continue our discussion of the matrix structure analysis, okay, or the stiffness method. So just a quick reminder, what's meant by the stiffness, okay? Stiffness, K, okay? It's the force required, okay, to have a unit displacement, okay, or to give a unit displacement. So, for example, here for a spring, okay, You put a force P, okay, there is a displacement U, so the relationship is that P is equal to KU, okay? P equal to KU over here. This is the stiffness equation. The force, okay, is equal to the stiffness coefficient multiplied by the displacement, or this stiffness coefficient is the, the force required to perform a unit or to give a unit displacement, okay? But this is, a spring. This is the simplest way of, representing this stiffness equation, P equal KU, expanding this to a beam element. That's what we did last time, okay? Having a beam element here, we don't only have one displacement that can happen, okay? At each node here, the start or the near end of the member and the far end of the member, there can be 3 degrees of freedom, or 3 movements. A horizontal movement, the vertical movement, and the rotation, okay? For beams, okay, we're starting our discussion with beams. So for beams, we're neglecting or we're not taking into account the horizontal displacement Qx, okay? So it's only a vertical displacement Qy, or we can call it delta, okay? So here we have 4 different allowed degrees of freedom, okay? 2 at the near end, the theta at the near end, and the delta at the near end, the theta at the far end, and the delta at the far end. If we want to write the stiffness equation, okay, so we have to relate the 4 forces here. Force, the vertical force at the moment here, the vertical force in the moment here, to the 4 displacement here. So actually, the stiffness equation, it's not just one stiffness equation, okay? It's a set of 4 equations, okay, relating the 4 forces to the 4 displacements, okay? So what we tried to do last time, okay, is trying to find those, coefficients that relates the 4 displacements, okay, the vertical displacement, this vertical displacement, and this moment, this vertical force, and this moment to the displacements here, the vertical displacement and the rotation, the vertical displacement and the rotation here. We did this step by step, applying a unit displacement and find what are the forces that results from this unit displacement and find the coefficients. In this case, 4 coefficients, so we did 4 steps. Every time we find the 4 forces, we apply a unit displacement here and find those 4 forces that, result from this unit displacement, and so on, okay? 4 different allowed displacement. Every time you apply one of those displacements, you find the 4 forces, okay, as we see here, and then we write this as, 4 set of equations. The force at the near end in the y direction is 12 EI divided by LQ multiplied by delta M, okay, delta at the near end, and this coefficient multiplied by theta M, the near end, and this coefficient multiplied by delta F, and this coefficient multiplied by theta F, and so on for the moment at the near end, the vertical force at the far end, the moment at the far end, okay? They are related to those 4 displacements, okay? So if we have 4 equations like this, okay, we can write them in a matrix form, okay? So writing this in a matrix form, we have this vector. We're going to call this the load vector because it has forces, or the force vector, okay? So here we have a P vector, it's 4 by 1, equal to K, a K matrix that has those coefficients. So it's 4 by 4. Multiplied by the 4 displacements, okay? The 4 displacement at the 2 ends, okay? So this is the load vector, this is the displacement vector, it has the 4 displacements, and what relates the forces, okay, or the loads to the displacements is the stiffness matrix, okay? So this is the stiffness matrix. It has 16 elements, okay? So now, this is where we ended last time, okay? So here we have P equal KU. K is not a number, it's a matrix, okay? That has those numbers, okay? So what does each of those numbers mean, okay? What does this number mean? This number, okay, is the force at the near end, okay? The vertical force at the near end due to a unit displacement at the near end, okay? What does this number means? It's the force at the far end due to a delta at the far end, a unit displacement at the far end. What does this element mean? It's the force at the far end due to a rotation at the far end. Okay? So now, this is called the member stiffness matrix. Okay, when we derived this, we just had one member. Okay, with two nodes, start or a near end, and an end or a far end of that member. Okay, so this is the member stiffness matrix. As we see here, when we derive this matrix, okay, we had EI as a general number, L is general, so this applies to any beam member. So this stiffness matrix, okay, matrix is constant for any prismatic element, okay, or any prismatic beam element, okay. What do I mean by prismatic? That the section is constant, okay, EI is constant throughout the length of the member, okay. So here, this is the stiffness matrix here. So now, let's see some properties of this stiffness matrix, okay? And generally, those properties are applied to any stiffness matrix, okay? So properties of the stiffness matrix. As you see here, one of the properties of the stiffness matrix here is symmetric. What does this mean? That this element is the same as this one. This one is the same as this one. This one is the same as this one. Okay? For example, this one is the same as this one. So it's symmetric according with respect to the diagonal. Okay? This one is the same like this one. This one is the same like this one. Okay? So it's symmetric. What does this mean? What does symmetric mean? That Kij is equal to Kji. Okay? That's the first property. The second property is that all diagonal elements are positive. As you see here, any element on the diagonal of this matrix is positive. Okay? It cannot be negative. You cannot, because these elements are the force, okay? They relate the same force, or the force and the displacement in the same direction. So this is the force, the vertical force at the near end, related to delta at the near end, the vertical displacement at the near end. You cannot, physically, you cannot have a force in a certain direction and the displacement goes in the other direction, right? This is the moment at the near end related to rotation at the near end. So you cannot apply a moment at let's say clockwise, and the displacement becomes counterclockwise, okay? So those has to be positive numbers, okay? Physically, they cannot be negative, okay? So this is one property here. Another property, or this is not a property, but like something that you can do for this stiffness matrix, okay? This can be subdivided. I can subdivide this K into a set of small matrices, okay? So here, if you look on this matrix here, it has 4 small components. It's 4 by 4, so it's 16 elements, but it has 4 small components. This part here relates the forces and the moments at the near end to the displacements at the near end, okay? This part relates the forces at the near end to the displacements at the far end. This one over here relates the forces at the far end to the displacements at the near end, okay? This part relates the forces at the far end to the displacements at the far end, okay? So I can subdivide my matrix into 4 small matrices here. K, okay, is a submatrix that relates the forces in the near end to the displacements at the near end. And this is 2 by 2. and the K that relates the forces in the near end to the displacements at the far end. Again, this is 2 by 2. And K that relates the forces at the far end to the displacements at the near end. And it's 2 by 2. And K that relates the forces at the far end to the displacements at the far end, and this is 2 by 2. So you can always subdivide, okay, your matrix into small sub-matrices, okay? So now, okay, the notation here that we used for those sub-matrices, and then we're going to generalize this to use with any, this notation, we're going to use it with any element or any sub-matrix. K and N, what does K and N? It gives, K and N is the matrix that gives the forces at N due to a unit displacement at F. Okay? And then K and F, what does K and F means? It gives the forces at N due to a unit displacement at, the first one here is at N, okay? Unit displacement at N, K and F. The second one, K and F, gives the forces at N due to a unit displacement at F. K Fn, it gives the forces at F due to a unit displacement at N. And then KFF, it gives the forces at F due to a unit displacement at F. Okay? So, as you see from this notation, okay, we can generalize this to any element or any submatrix, okay? So generally, we can use the following notation. When I say K, X, Y, whether it's an element or a submatrix, okay? What does this mean? K, X, Y. It's the force at X due to a unit deformation at Y. Okay? So this is the general notation that we're going to use. Kxy is the force or the stiffness element that relates the force at X with the deformation at Y. Okay? So now, what we did is we tried to write the stiffness equation, but just for a beam element. Okay? What if we have a structure that has more than one element or more than one member? Okay? How would we write the stiffness equation that relates the forces at the nodes to the displacements at those nodes? Okay? So now we would like to generalize this to structure. Okay? So now let's generalize this concept of stiffness matrix to a structure as a whole, not just an element. No, we want to write this for an entire structure. So to do this, let's do it on an example. Okay, no numbers, but just to understand, how to do it and what's the problem that we have here. So let's say now you have a beam that looks like this. Okay? So this beam now, okay, how many elements do you have? How many beam members do you have in this beam? 3. So the first thing that we're going to learn here to label our elements, okay, or our members, okay? This is exactly what happens, or what the softwares, like the STAT software or the SAP software, any finite element software does here, okay? So you start labeling the elements, okay? You remember our last time in the computer lab, okay? You had this table, okay, of elements, okay? When we were dealing with the STAT software, you have numbers for each, okay, member. So here, we start by labeling our elements. So this is element 1, or beam member 1. This is beam member 2. This is beam member 3. We're going to put them in rectangle, okay? In rectangles. Each of those elements have start point and an end point, okay? So let's label the nodes here. How many nodes do we have here? 4. This is node 1, node 2, node 3, and node 4. Okay? So we have 4 nodes. We're labeling them the same numbers 1, 2, 3, 4, but we're putting them in circles. Okay? So we have 4 nodes and we have 3 elements in this problem. Okay? At each node, there can be 2 motions, right? Generally, there can be 3. A vertical motion, or a vertical displacement, or horizontal displacement, and a moment, right? Or a rotation. But for beams, we're neglecting the horizontal displacement. We're saying that no horizontal displacement, okay? So at each node, there can be 2 degrees of freedom. A vertical motion, or a vertical displacement, and a rotation, okay? So how many degrees of freedom that we have here? 8, right? Total 8 motions that can happen. But definitely some of them are restricted or constrained. They cannot happen, okay? So let's write this problem here. Each of those elements, okay, first, okay, it has a length. So this element 1 has a length L1, and it has an EI, let's say 1. And this element 2 has a length L2 and an EI2 that can be different from member 1. The third member here has a length L3 and EI3. Okay? So now, for the shown beam, what we discussed here, the shown beam has 3 members, and we're going to denote them by the numbers in squares, okay? And it has, and this structure has 4 nodes. We're going to always denote them by circles. This is the notation that the book used, but anyway, you don't have to, be strict about it, but anyway, just to be consistent, okay? So this is what we have here. And then at each node, there are 2 degrees of freedom. A delta, a vertical displacement, and a theta. So for the entire structure, we have 8 degrees of freedom. What are those 8 degrees of freedom? A delta and a theta at node 1. So delta 1 and a theta 1. A delta and a rotation at node 2. A delta, a vertical displacement, and a rotation at node 3. A vertical displacement and a rotation at node 4. Those are the 8 degrees of freedom that we have. Some of those are known. And some are unknown. So what are the known degrees of freedom? What of those 8 degrees of freedom are known?
Theta 1, theta 2.
Theta 1 and theta 4. You know their value. How much?
0.
0. Any other thing that is known?
Those fixed supports.
Those are fixed supports. Those are pivot supports.
Only up to those settlements.
Yeah, there is no settlement, so delta 1, delta 2, delta 3, delta 4 are zeros. They cannot move vertically, upwards or downwards, okay? So you have 8 degrees of freedom, but you know 6 out of them. Delta 1, theta 1, okay? And delta 2, and delta 3, and delta 4, and theta 4, okay? Those are zeros. Okay? Exactly as we did in the, slope deflection method, okay? We had those, kinematic degrees of freedom. We were just counting the unknowns. But here, I have 6 that are known. They are zeros, okay? And now the unknowns one. What are the unknowns degrees of freedom? They are theta 2 and theta 3. Okay? So, since we have those 8 degrees of freedom, okay, we can have 8 forces. Okay? Force and the moment here, force and the moment here, force and the moment here, force and the moment. Okay? So, the number of the forces is equal to the number of the degrees of freedom. Okay? So, similarly, we have 8 forces. What are those? A vertical force at node 1, a moment at node 1, a vertical force at node 2, a moment at node 2, a vertical force at node 3, a moment at node 3, a vertical force at node 4, and the moment at node 4. So 8 forces. And again, similarly to the displacements, some displacements were known, they were equal to 0, and some displacements were unknown. The forces also, those 8 forces, some of them are known and some are unknown. Okay? So what are the known ones and the unknown ones? Okay? So some forces are known and some are unknown. You have here a reciprocal relation between the forces and the displacement, okay? What does this mean? If you know a displacement at a point or at a node or a certain degree of freedom, you don't know the force at that degree of freedom. And if you don't know the displacement, you know the force, okay? So actually, I'll just copy those and write the reciprocal of them. Copy. I'm just going to paste them here. So the unknown, instead of degrees of freedom, the unknown forces, okay, will be the opposite of the, unknown degrees of freedom. So here you had theta 2, okay? So let me undo this. Okay. So here you have the unknown degrees of freedom. They will be similar to the known forces, okay? So They are reciprocal to each other. The unknown degrees of freedom. We're just going to remove this and put the known forces. Theta 2 was unknown. So that means that M2 will be known. Theta 3 was unknown, so M3 is known. Okay? Here you have those where the unknown, the known degrees of freedom. That means that the equivalent forces are unknown. So I'm just going to remove this and put the unknown forces. Delta, so that's equivalent to Fy1. Theta 1, so that's M1. Delta 2, so Fy2. Delta 3, so Fy3. Delta 4, so this is Fy4. Theta 4, so that's M4. And those are unknowns. Why are those unknowns? Fy1 is the reaction here. Do you know this reaction? No. M1 is the moment here, the reaction here. You don't know how much is this. Fy2 is the reaction of this support. It's unknown. Fy3 is the support of this reaction. It's unknown. Fy4 is the vertical support here. M4 is the moment here. Those are the support reactions. You don't know them, okay? Before solving the problem. The moment here, okay, will come from the applied loads. If you have an applied load, so it's going to be equal to the moment that is here. So you would know how much is M2. You would know how much is M3 from the applied loads, okay? So those are the support reactions and those come from the applied loads. Okay? So now I have 8 forces, those 8 forces, and I had 8 displacements in the entire structure. Okay? What we need to do is find a relationship between the displacements and the forces. Those 8 forces and 8 displacements. What is the equation that relates forces to displacements? What did we name this? An equation that relates forces to displacements. The stiffness equation, P equal Ku. The force is P is equal to K, stiffness coefficient, multiplied by U, the displacements. Okay? So now, the relationship between the forces and the displacements can be written in terms of the stiffness matrix. Simply P, the forces, is equal to Ku. How many forces do I have in this problem? 8, right? So P here, it's 8 by 1. It's a vector that has those 8 forces. Those 8 forces are the forces that I have in my structure at the nodes, okay? And U, how much is U? It's 8 by 1. It has the 8 displacements at the nodes. I have K here that relates those P to those U. So what's the size of K? 8 by 8. So the size of the stiffness matrix, okay, depends on the you know, the geometry of your structure. It can be 8 by 8, 12 by 12, 64 by 64, but it's a square matrix, okay? The more nodes that you're going to have, right, the larger your stiffness matrix is going to be, okay? That's why you need computers. For example, for the steel bridge, okay, that we modeled last time instead, okay, just count the number of nodes. Do you remember how many nodes we had, okay, in the model that we, 100 and something, right?
Yeah, we're 400.
Too many. Too many.
I think we got around 400.
400 nodes, right? At each node, how many degrees of freedom are there? 2 if it's a two-dimensional structure, and if it's a beam, but that one is a frame, okay, so you have 3 degrees of freedom at each node. If it's two-dimensional, but actually it's three-dimensional, so you have 6 degrees of freedom, okay? So 6 times 400, so the stiffness matrix is 2400 by 2400, okay? That's what the stat does, okay? It just builds this overall stiffness matrix, okay? That is 2400 by 2400, okay? You can do this by hand, okay? But you know how to do it, okay? How does the computer do it, okay? The same way that we're doing it here, okay? So how to build this K, the 8 by 8 stiffness matrix, okay? So here, P, let's write the 3 matrices first, okay? P, which is 8 by 1, this is the load vector. And this has the 4 forces, Fy1, M1, Fy2, M2, Fy3, M3, Fy4, M4. This is the load vector, okay? And then for U, which is 8 by 1, this gives the displacement vector. It's not a matrix, or it's a matrix, but it's a, you know, one-dimensional matrix, so it's a vector, the displacement vector here. It has an 8 displacements, U, or delta 1, theta 1, delta 2, theta 2, delta 3, theta 3, delta 4, theta 4. Okay? This is the displacements, okay? And then we have this K matrix. K, which is 8 by 8. Now, this K is for the entire structure. So now we're going to call this the overall stiffness matrix. Okay? It's for the entire structure. To differentiate this from what? From the element stiffness matrix. You remember last time and today we started by writing this. What's this? This is the element stiffness matrix. A beam element stiffness matrix is just 4 by 4. While the overall stiffness matrix for the entire structure, it can be any size depending on the geometry of the structure. Okay? So now we have the overall stiffness matrix. It's 8 by 8. Okay? So it's an 8 by 8. Okay? But now this K relates those P with those U. Okay? So it relates forces to displacements. Okay? Exactly like this one did. It relates those forces to those displacements. Okay? So now let's label our overall stiffness matrix. It relates 8 forces to 8 displacements. So what are the forces? It relates Fy1, M1, exactly the same arrangement that I had for my load vector. Okay? Fy2, the same order as in my load vector. Fy3, M3, Fy4, M4. And it relates those to the displacements, the nodal displacements. Delta 1, theta 1, delta 2, theta 2, delta 3, theta 3, delta 4, and theta 4. Okay? So this is my 8 by 8 overall stiffness matrix. It relates those 8 forces to those 8 displacements. It's 8 by 8, so it has 64 elements. Our target now is how to find those 64 elements, how to build this matrix, how to find the numbers there. Okay? What numbers do we put here? So we're going to name those, let's say, K11, K12, K13, K14, K15, K16, K17, K18, right? And then the second row, third row, so K21, K22, K23, K24, and so on, okay? So how many elements do you need to find to build this matrix? 64, right? Is it 64? No, it's less than 64. Why? Because this matrix is symmetric, okay? It's symmetric about the diagonal. Oops. Members here. So K33, K44, K55, K66, K77, K88. So it's symmetric about this diagonal. Those elements here are the same as those elements here. K21 is equal to K12. K13 is equal to K31 is equal to K13. K21 is equal to K12 and so on. Okay? So K21, okay. So it's symmetric. Okay? Kij is equal to Kji. Okay? So you have to make sure also when you build this, those elements have to be positive. Okay? This is a check for you. Those elements are always positive. And this part here is symmetric. Okay? So now our question is, this is the most important part now. How do we build the overall stiffness matrix? How to find those elements? Okay? So to do this, we're going to do it on steps. The first step, that's an easy one, okay? We first have to build each member's stiffness matrix. How many members do we have in this problem? 3. So I have to write the stiffness equation for each member separately. Okay? So for example, let's do this. So for member 1, okay, we need to build K. We're going to name this K1, the stiffness, the element stiffness matrix, okay, for element 1, for member 1. How does this look like? We did this before. This is the stiffness matrix that relates forces and displacements for an element. okay, at the ends of an element, right? You agree with this? So this is the stiffness matrix for each member that we have in our problem, okay? It looks like this. So I'm just going to copy it here. And paste it here. Now, I just copy and paste, okay? Is that correct? Do I need to make any changes here? Just small things here. EI is EI of element 1. L is the length of element 1, okay? This is, those numbers all are of member 1. That's all, okay? EI1, L1, EI1, L1, because the elements that I have, they don't all have the same length and the same EI, okay? What's also different? These numbers of those stiffness elements, okay, we're relating forces to displacements. What are the forces and the displacements? The forces were the vertical force and the moment at the near end, the vertical force and the moment at the far end, and the displacements are similar to them, right? Now, for element 1, what is the force at the near end and the moment at the near end? What did we call those? This is element 1. Where's the near end of element 1? It's node 1, okay? So this is delta 1 and F, delta 1 and theta 1, okay? Instead of delta N and theta N, those are node 1 now. I labeled them node 1, okay? And the forces are also at node 1. So here, this, I'm just going to mark those FNY1, MN1, 2, 2, and those are delta 1, theta 1, delta 2, and theta 2. Okay? And then I'm going to build the stiffness matrix for member 2. K2, this element stiffness matrix for element 2. I'm just going to paste the same matrix here. But when I put EI, I have to use EI and the length of member 2. Right? Okay? This is member 2. It has a different length, has different EI. You have to use the EI and the length of member 2. And now, K2 is relating forces to displacements. What forces and what displacements? 2 and 3. The start here, the near end of member 2. This is member 2. The near end or the start is node 2, and the end is 3, node 3. So it's actually relating the displacements and the forces and the displacements at node 2 and 3 together. So this here is 2, 2, 3, and 3. And then here, those are 2, 2, 3, 3. Okay? And then I'm going to do the same for member 3. Just pasting the same matrix here. Now this, I just have to put EI and the length of member 3. What forces and displacements are those relating to? 3 and 4. Okay? Now, what did I do? My target is not to find those. My target is to find what? The overall stiffness matrix. The factors here that relates delta 1 to Fy1. Okay? This number here that relates delta 1 to M1. This number here that relates delta 2, okay? Which, let's say this number here that relates M1 to theta 2, and so on. Okay? How would you find those numbers? Okay? You just map, okay, the numbers from your element stiffness matrix to the overall stiffness matrix. So for example here, this number relates theta 1 to Fny1. Okay? So I'm just going to take this number and put it here, theta 1 and Fy1. This is the number that comes from this matrix. Okay? And so on. Okay? So let's see some examples here. So this is the second step. We just map the numbers from the element stiffness matrix, okay, to the overall stiffness matrix. Map each factor in the overall stiffness matrix to its components in the members stiffness matrices. So let's see some examples here on doing this. So for example, K44, okay, in the overall stiffness matrix, where's K44? This is K44. What does this relate? It relates M2 to theta 2, right? So K44 relates M2 to theta 2. So now I'm just going to go and scan my stiffness matrices. Where is the elements that relates M2 to theta 2? Okay? Here. I have M2, okay? And theta 2. This element here. Or EI1 divided by L1. Okay? It comes from the stiffness matrix of element 1. Yes?
Is that the same as in the next one?
The same as what?
Because isn't K44 things it's into theta 2? Isn't there two matrices that you can? It's going to be in this one and then it's going to be in the next one. It's the far side on this one. And
Okay, we're going to see that. Okay? So we have here M2 and theta 2. So we have this element, 4EI divided by L. Okay? So we have here this interaction is found in member 1 stiffness matrix. And is equal to 4EI1 divided by L1. So is this type of interaction found in another matrix as well? You said yes. In K2 here, we have M2 and theta 2 here. And it's 4EI2 divided by L2. Okay? So it's also found in members 2 stiffness matrix and is equal to 4EI2 divided by L2. So to build K44, when you use this one or this one?
Is it the lengths or equal on this one?
They are not equal, right? The formula looks the same, 4EI divided by L, but this is the length of member 1 and the inertia, the moment of inertia of member 1. This is the length and the moment of inertia of member 2. They are not, they don't have to be the same. Which one would you use? Both. Add them together. Why add them together? Just to solve this problem that, okay, I don't know which one, just add them. You remember? Not 0. You have to add them. Why? I'm just going to scroll up to what we did in the previous lecture. You remember this example here? When we started, we said if you have just this spring, so the relationship is P1, okay, is equal to, this is, okay, P1 is equal to K1U1, or KU, and P2 is equal to K2. So this is, let's see here, this is P1, and this is P2, this is K2, okay? I have those here. Okay, yeah, no, that was correct. P2, okay? So P1 is equal to K1U, and P2 is equal to U, K2, okay? So when I have both together, okay, P, the summation of the forces, is equal to K1 plus K2U. So I just have to add them together. If there are two members contributing to the stiffness or the motion of that point, okay? This node is connected to this member and this member, so I just have to add the stiffness matrices, or the stiffness numbers, the stiffness coefficients. If I had those three here, so P is equal to KU, K is the summation of those three Ks, right? This is what we learned last time, okay? So simply here, you just add all the contribution that comes from any member that is connected to that node. Okay? So, therefore, here, K44 is equal to the summations 4EI1 divided by L1 plus 4EI2 divided by L2. Okay? You just have to add them together. Is there a contribution that comes from member 3? Is there M3 here? Sorry, M2. Is there M2 here? No. So there is no contribution that comes from member 3. The contribution only comes from member 1 and member 2. Okay? Let's see another example here. let's say K23. Where's K23? K23 is this element. It relates M1 to delta 2. Okay? So K23 relates M1 to delta 2. So let's look on the 3 element stiffness matrices. We said this is M1 to delta 2. Is there contribution here from the first matrix here? M1 to delta 2. Yes. Okay. So K23 is equal to that element plus what contribution I get from the second element stiffness matrix. Is there M1 and delta 2 here related together? Is there M1 here? No. So there is no contribution from the second stiffness matrix. Is there M1 and delta 2 here? No. So it's just that element. Okay? So only here. Member 1. Will have a contribution. And therefore, K23 is equal to negative 6EI divided by L of member 1. Okay? Let's see another example. K26. Let's see here. K26. Where's K26? K26. And it's equal to K62, by the way, right? Symmetric. K26 relates what? Relates M1 to delta 3. It's the force at M1 or M1 due to a unit displacement at theta 3. Okay? M1 to theta 3. So this one relates M1 to theta 3. Let's see, where does the contribution come from? Let's see, get the number from the 3 matrices here. M1 to theta 3. Where's theta 3 here? There is no theta 3. No contribution from this matrix. M1 to theta 3. There is theta 3, but there is no M1 here. Hmm? No. There is no relation between M1 and theta 3 from this member. Okay? M1 and theta 3. There is a theta 3. Is there M1 here? No. So what would you do for this element? It's 0. There is no relation between the force M1 and theta 3. A unit displacement at 3 or a unit rotation at node 3 will not give you a moment at node 1. Okay? So it's 0. There is no interaction here. So therefore, K26 is equal to 0. Okay? So now you can go ahead and build your overall stiffness matrix, element by element. Those 64 elements, you go ahead and build them one by one, right? Just by mapping the elements, okay? Some of them will be zeros, okay? But some will not be zeros. So now we can build K, okay? Let's name it K capital, the overall stiffness matrix. We use K capital, okay? So now once you build it, it would be very nice to rearrange it, okay? So now, I just need to rearrange this. Originally, how was it arranged? It was relating the overall stiffness matrix here. Was arranged like this. This was the order, Fy1, M1, Fy2, M2, Fy3, M3, Fy4, M4. Okay? This is the same order. Delta 1, theta 1, delta 2, theta 2, and so on. Okay? Can I shuffle this a little bit? Yes. Because what's this? It's just a set of equations, right? So for example, let's say here, this, I'm just going to erase this, but just as a simple example here. If I tell you I write two simultaneous equations like this, okay? 4 is equal to 2x1 plus 3x2. And then 3 is equal to 6x1 plus 4x2. Does it make any difference if I write those equations like this? 3 equal to 4x1 plus 4x2 plus 6x1, and 4 is equal to 3x2 plus 2x1. Did I make any changes here? No, I just changed the order, okay? But it's the same two equations, okay? I can change, if I write this in a matrix equation, okay? In matrix form, this is 4, 3 equals to 2, 6, 3, 4 multiplied by x1, x2, right? What I did here, I changed this. This is 3, 4 equals to 4, 6, 3, 2 multiplied by x2, x1. But it's the same two equations, right? I can change the order. There is no problem. It's up to me, right? So, as long as you keep the numbers correct, okay, you can shuffle them, you can play with the numbers, just change the row. Let's say you have the first row, you know you want to put this as the sixth row. That's fine, okay? So now, this is what I'm going to do here. I'm going to rearrange my matrix, okay? I want to group the known forces together, or the unknown displacements together, and the known displacements together, right? In this problem, we had 6 known displacements and 2 unknown displacements, right? I want to have my 2 unknown degrees of freedom, or 2 unknown displacements first, okay? So here, I'm going to start with the unknown displacements, where the rotation at node 2 and the rotation at node 3. So M2, M3, okay? And then here I'm going to put the rest here. M1, Fy1, M1, Fy2, Fy3, Fy4, and M4. And that's equal to the K matrix, which is 8 by 8. But now this is arranged differently, right? Originally it was M1, sorry, FY1, M1, right? FY2, M2. Now I just rearrange them, okay? And this is related to the displacements here. So the displacements here, I just had theta 2, theta 3, and then delta 1, theta 1, delta 2, delta 3, delta 4, and theta 4. Okay? I just rearranged them, that's all. How did I rearrange them? Here I have the unknown displacements first. So those, I grouped the unknown displacements first. So here, those are the unknown displacements. And those are the known displacements. Right? You knew those are zeros, right? So I just put my unknown displacements first, and then the known ones, okay? Now, the forces are the opposite. Those are known forces, and those are the unknown forces. Right? This part is 2 by 1. This part is 6 by 1. Overall, it's 8 by 1. Right? So simple, right? Now, my stiffness matrix here, it's 8 by 8. I will subdivide it, okay, into small sub matrices. This one, it's 2 by 2, okay? This part here is 2 by 6. This part here is 6 by 2. This part here is 6 by 6. Right? Okay? So now let's name this K11. Okay? This one is, or let's okay, K yeah. K known, K unknown. Okay? It relates the known forces to the unknown displacement. This one, it relates the known forces to what? To the known displacements. Right? This one here relates the unknown forces to the known displacements. This one relates the unknown forces to the unknown displacements. Right? Now, the stiffness matrix, okay, is a deformation method, okay, or a displacement method. What does this mean? Is that to solve your structure, exactly like the slope deflection method, you need to find the displacement. So my problem here, I need to find those, theta 2 and theta 3. Once I find them, okay, I can solve my structure, okay? So I need to find those unknown displacements. So I will just write or use this equation here. For a matrix, okay, this part is equal to this times this plus this times this, right? This is how you do matrix multiplication, right? This part is equal to the row times the column, right? So this part times this part plus this part times this part. How much are those numbers? 0. So you multiply this by 0. What will you get? 0, right? So simply I can have just those two parts. Okay? So I have here M2, M3, which are known, by the way, right? It's equal to K, Ku, which is 2 by 2, okay? Multiplied by theta 2, theta 3, plus K, Kk, which is 2 by 6, multiplied by theta unknowns, sorry, knowns, the known thetas, which is 6 by 1, but this one is what? 0, right? So this term cancels here. So simply, we end up having this part. Okay? What does this equation tell you? You have a matrix, okay? M2, M3, the vector, the load vector, that you know those values, right? Those are the known forces. You know this Ku, okay? The first 2 by 2 matrix, which you have the numbers. You build this matrix, right? We learned how to build this, right? Equals to those unknown displacements, multiplied by those unknown displacements. So this is equal to this multiplied by the unknown displacement. Can you solve for theta 2 and theta 3? How to find theta 2 and theta 3? So therefore, theta 2 and theta 3 is equal to K, Ku inverse, the inverse of that matrices multiplied by that matrix. And that's it. This is how you solve for your unknown displacements. Right? Matrix multiplication, just matrix multiplication. This is how the STAD or any finite element software solve for the displacements. It's just, the thing is, it's a computer, so it can do this for hundreds and thousands and maybe 100,000s of, displacements or degrees of freedom. Okay? Any question here? So the thing is, to find theta 2 and theta 3, did you need all those numbers? The 64 elements, do you need to find all those 64 elements? No, you just needed those 4 elements. That's it. That's what you need. You don't need the 64 elements. Don't waste your time finding the 64 elements, right? Just 4 elements is enough. Okay? Now, once you know theta 2 and theta 3, let's say I ask you, how much are the reactions? Where are the reactions here? Those are the reactions, right? The unknown forces are the reactions, right? So how can I find this from this matrix? This part is equal to this matrix multiplied by this. This is now known, so you need to multiply this by this. And then this part multiplied by this, right? How much is this? 0, right? So you don't need to know this part, but you need to know this part. 6 by 2, if you need to find the forces. Okay? So now, you solve this equation, solve to find the unknown displacements, and then to find the unknown forces you have the unknown forces, which is 6 by 1 is equal to K unknown known, which is 6 by 2, times U unknown, which is now known, right? You know the displacements, you solved for those now. This is found in the previous step. This is how you solve for the displacements and the reactions using the stiffness matrix. Okay? It's all revolving about building this overall stiffness matrix. You have to build it correctly, and that's it. And then it's all matrix equations that you're solving together. Okay? Any question here? Okay, so see you next week.
We can get 60% of our design project now of this, and then we'll do retaining wall for 4 lectures.
Yeah,